basics of spin. This is this you need to kind of keep in mind as you go along. And as I mentioned, under some conditions, you need that full spin-out framework, and in some cases, no. Right? And lot of it depends on whether you can just get by with the diagonal elements, or are there off-diagonal elements to worry about. And in some sense, it is. I always say this spin is a very good example in terms of illustrating the relationship between quantum and semi-classical, but in a relatively simple context, because spin has just two components. Usually a wave function has many, many components, and it's in a way like a giant spin. It's just not just two components, but hundreds of them. So in general, when we write G sub n, it's a huge matrix, because you might have 20 things here, another 20, so 40 by 40. So in that sense, it's then a 40 component spin, right, with all kinds of off-diagonal elements. And by and large, the whole idea of that when can you get by with a semi-classical picture? Well, when you don't have to worry about off-diagonal things. So you don't have to worry about matrices at that point. And so it means when you write a Gn, here's a matrix. If you can just get by with the diagonal, then semi-classical picture, your intuition and normal things work. Anytime off-diagonal is important, it doesn't work very well. And of course, when does it work? Well, it's also that your choice of basis is kind of important in that thinking. That if you're thinking of electrons and solids, if you're thinking in real space, things may not be diagonal. If you think in K-space, it may be diagonal, etc. In this context also, supposing your spin points in the x direction, then of course, Gn, as we discussed, looks something like this. And you got off-diagonal, serious off-diagonal elements. But if everything's in the x direction, then that's kind of an unnecessary complication. Because what you could have done was chosen your z along that x direction. And then everything would have looked, then things would have looked more like this, or maybe zero here. Because basically it's all pointing in one direction. So with a proper choice of basis, you can make things look diagonal. And so if you choose your basis this way, then everything would be relatively common sense. You can understand what happens. If you choose your basis like this, okay, if you do things mathematically and take a trace at the end, you'll get the same answers. But if you try to think, you'll get all confused because of the matrix part of it. Right? So the spin kind of illustrates a lot of these subtleties very nicely. So now, in the field of spintronics, as I say, generally speaking, when you have normal electronic devices, spin plays a very passive role. It's basically just 2 degrees of freedom. So you have to multiply by 2. So it's like if you didn't have spin, the quantum of conductance would have been 25 kilo ohms. You have spin, so it's 12.5 kilo ohms. That's it. Right? Because there's all this coming in parallel. You just have to remember to multiply by 2 at the end. But spintronics is generally the important developments that made it relatively, lots of new discoveries, lots of interesting things happening, especially in the last 10 years, and maybe last 20 years, you could say, is because people are able to control the spins individually. And it kind of all started with this basic demonstration that if I have a channel and you have magnetic contact, if the 2 magnets are parallel, you have a certain resistance. If they're anti-parallel, you have a higher resistance. That's the basic demonstration. And in the original experiments, or in the early experiments, people were using what would be called spin valves. Spin valves meaning where this is a metal, like copper, and these would be magnets like cobalt. These days, I think people use, instead of copper, they use the insulator here, a thin insulator, and then they call this a magnetic tunnel junction, MTJ. So that's a word you'll see a lot. NTJs. And these were the first devices that showed how to inject one type of spin preferentially compared to the other. And later on, another effect was demonstrated, which was very important also, and that is how using spins you can turn a magnet. So the idea was that, okay, to start with, you can use this to read information. So if the magnet is this way, resistance is low, magnet is this way, resistance is high. So you measure the resistance, tells you which way the magnet is pointing, which means you have read the information. And this had a major impact on the storage industry because it allowed you to make very compact read heads, right? Which was important for, as you know, there's all this that's stored on magnetic disks. All the stuff on YouTube, that's all on magnetic disks, and the only reason you can store it in a reasonable space is because you have terabits per square inch, these magnetic disks. And of course, terabits per square inch also means you have to read it with that kind of resolution. And that was made possible by reading devices based on this principle. So it had a major impact, which was recognized with the Nobel Prize about 10 years ago. Then came this thing that, okay, this is how you read it, but how do you write? When you're writing the information, usually you use a magnetic field. So how do you turn a magnet? The classic method is have a coil that creates a magnetic field. What is now demonstrated is that supposing you have a magnet like this, and you put a negative voltage on this side, so you inject electrons. So the magnet being this way, let's say you're injecting spins in this direction, and these spins come here, and when they hit this magnet, they tend to turn the magnet upward, back in the same direction, so because of their interaction with this magnet. And the idea is that if the current is large enough, so you hit them with enough spins, then at some point you will be able to turn it back. Of course, you couldn't do this if it was a thick magnet. You can only do it if it's what you call a nanomagnet. Nanomagnet means the area is large. So area could be microns, but thickness is small. Thickness is like 1 or 2 nanometers. Because this whole thing is a surface effect. The spins come, hit the surface. If this is 1 micron thick, no way. Just hitting it with spins won't turn it. But nanomagnets, you can turn it. And that's the spin torque effect. And that's now, again, I think it's getting to the point where it is getting into real devices. So you'll see the word STT MRAMs. So MRAM is this magnetic access memory, and STT is spin transfer torque. So this is a whole new physics that's now very much getting used. Because as I say, 20 years ago, only way to turn a magnet would have been with magnetic fields. Now you can turn magnets with spins. Other interesting thing is that, yeah, if you apply a voltage, of course this turns to this. What is not as obvious is that if instead of a negative voltage I put a positive voltage here, what that means is I withdraw the spins, then with current again you can turn it back. So it actually works both ways. So it's not that you can just turn it into the same direction, you can reverse it also. So it can actually be used for writing information going either way, just through the spin current. Now, all of these devices then, if you wanted to model it from, again, atomistic type of models, then NEGF is something one could use in this context. It is used, actually. And question is, how would you do this? Well, just to see the basic principle, you could say, well, let's just, as you know with NEGF, I've said first thing you need to do is write H. And for this discussion, let's assume I have a really small device, just 1 point, which means H is just a 1 by 1 matrix. Okay? So 1 by 1 is just epsilon, whatever that is. Except that, I mentioned earlier, whenever you put in spin, you got an up spin and a down spin. So it's actually a 2 by 2 matrix. Now, the next thing you need to write is this sigma 1, and then there is sigma 2. Now, and as I mentioned before, there's this gamma, which is I sigma 1 minus sigma 1 delta. And this gamma is a measure of how easily electrons get in and out. It's this imaginary part of sigma. Because the real part of sigma only shifts your energy level. It's the imaginary part that represents things going in and out and effectively broadens the level. So, in general, your sigma, if it is say minus I gamma over 2, then the corresponding gamma would be, I think, you'd get gamma. So, corresponding to a, if this is gamma, this would be more like minus I gamma over 2. That's I think what I'm trying to say. Right? Now, so if this was normal contact, then you could have written the sigma something like this. Because you could say, okay, up spins get out into the contact at the rate of gamma, down spins get out at the rate of gamma. You can put that in. And the corresponding gamma matrix would have looked like gamma. Now, what do you expect with a magnetic contact? So the magnets are pointing in this direction. And basically, you can kind of guess what you should have. It's like, because the magnets in this direction, there's a lot of density of states or modes for upspin, very few for downspins. And so, what will happen in a magnetic contact is, those two things won't be equal anymore. It will be more like alpha, beta, where alpha is greater than beta. So, basically that's what it is. And the same on this side. So I guess I should have written here minus I alpha over 2. So here I'm just trying to do a simple model with these numbers. If you actually, in a given microstructure, calculated sigmas, you might get some real part here also, etc. I'm just trying to do the simple thing. Now, if you have parallel magnets, then this side will also look the same. So when I write gamma, it would look like alpha So if I take this, and if I want to calculate the conductance, and let's say we're doing the coherent transport, okay, then you do this thing that we went through last day, which is trace of gamma 1, GR, gamma 2, dA. Most of that are discussion. And that then would give you the conductance for the parallel configuration. The question is, how do you find the anti-parallel one? So let's say this magnet is what it is, but this one, instead of being parallel, I have now reversed. Any thoughts on what that might be? So it means I don't need to mess with gamma 1, but I need to change gamma 2. So what should gamma 2 look like? Go ahead. What you might guess is that the alpha and beta will get interchanged. Because now it's the downspin that gets out easily, upspin does not. So alpha and beta will get interchanged. So there is the anti-parallel configuration, that's this one, and then there is the parallel configuration, which is this one. And you could go through and get the trace and all that. And I think that's actually done in the video lecture, so you can look at the details. But the main point I wanted to make is, you can relatively easily see that at the end of it, the parallel resistance would be lower than the anti-parallel resistance. Let me explain how you would see that. Because what you could do is, it's trace of these things. So to do it properly, I would have to write down the GR and GA. But let me just look at gamma 1, gamma 2. That kind of roughly gets you the idea. So with gamma 1 and gamma 2, thing is I'm going to multiply this with this. So if I'm doing the parallel configuration, let me write here. If I'm doing the parallel configuration, then it would be alpha squared and beta squared. And then of course I'm tracing it, so I'm adding them up. So at the end of it, it will be something like alpha squared plus beta squared. Whereas if I'm doing anti-parallel, I get 2 alpha beta. And now the point is, what you can show algebraically is that this is always bigger than that. Do you see that? Because if I subtract this from this, you get alpha minus beta whole square, which is always a positive quantity. So this is always bigger than this, which means that the conductance of the parallel configuration is always greater than the conductance of the anti-parallel configuration, and resistance is inverse, of course. So this model will generally fit that observation and would give you a sort of an explanation of how you could model this, understand. Now the trickier question conceptually is how to handle this one. And actually the real world read devices that I mentioned, the ones that are used to read information from storage disk, actually operate like this. In the sense that the way it works is, you have a fixed magnet here and another magnet like this, which is relatively soft and can move. And the thing is that you have this storage disk which has all the information stored in magnets like this. So you have a magnet here, a down here. And when this is held above this one, this magnetic field kind of pushes it upwards somewhat. When it's on something like this, it's pushed downwards. Now, when it goes upwards, it kind of becomes a little parallel, so the resistance goes down. Here it becomes a little anti-parallel, so the resistance goes up. And that is really what you sense. So that's how all the reed heads usually work. So it's not like you are actually parallel or anti-parallel, in fact more or less like this. Okay. But in any case, of course, this is an important conceptual point that I tried to stress before, that a lot of these spin-related stuff is easy to understand if everything's in the same direction, up, down, etc. Anytime you're halfway, that's when the subtle things come up. So something like this. Question is, okay, obviously this matrix is good. I've done nothing to that contact. But what do we do about this one? So let me first just state the answer and then we'll go on. I believe the answer is, in this business we'll see this Pauli spin matrices that we talked about. This one. This comes up in all various places. So I believe that in general the answer is this. The gamma will be something like alpha plus beta over 2 times I think that's true. Where n is the direction of this magnet. Let me just check quickly if this works for the two cases we wrote down. So could you help me? So supposing
Sigma Z.
does that look right? Yeah, please. Yes. Sigma Z. Okay. So if it's pointing in the up direction, then it will be plus sigma Z. No, I don't think I wrote it correctly. So what I should have done, I think, is to I plus alpha minus beta over 2 sigma Z, or sigma dot n eventually, for the moment sigma Z. Now see if that works. Okay. Let's see. Did that work? Because I is 1, 1, 0, 0. Sigma Z is 1, 0, 0, minus 1. Now does it work? Because if I look at the upper diagonal, this one, it's this plus this, which is alpha. Exactly as it should be. When it is, look at the lower one, it's this minus this, and then it's beta. That works. And similarly, if the magnet were pointing in the opposite direction, then I'd have put a minus there. And then I'd have got this one. Because then for the top one you'd be subtracting, and the bottom one you'd be adding. Okay? So the two limits work. So I think that's the right answer. So actually, the way people write it is more generally something like this. You pull this out, and inside you write I plus alpha minus beta over alpha plus beta, and then sigma dot n. So I think when I wrote it last time, I missed that factor. And this is what's often called the polarization of the magnet, because that is a measure of how good the magnet is in terms of discriminating between the two spins. Because if alpha is equal to beta, that's just a normal contact. It's not discriminating between the spins at all. It's not getting anywhere. So this is what you usually call the polarization of the magnet. So you'll often see this written as I plus sigma dot P. Where what is P? Well, magnitude is the polarization, n is whatever direction it points in. So that is the expression you will often see. Instead of this, people will write it like now, how do you justify this? Well, there's various ways of doing this. One way you can see is, if you accept this, then it will follow in a relatively straightforward way, if you accept this. Because then what I would argue is that supposing I have a magnet that's pointing in that n direction, then of course if it was in the z direction, then I know how to write it. I write alpha, beta, this is plus z, this is minus z, plus z, minus z. No problem. Now, what do I do if it's in the x direction? What I could argue is that if I were using plus x and minus x as my basis, then it would look like this. Except that I want it in plus z and minus z basis, because everything else, all my other matrices are in that basis. So I can't work with one thing in this basis. So I need to transform it. And the rule for transformation is, basis transformation says, you do, this v times v dagger. So whatever you need to transform x into z. And so what you write here is a matrix that expresses plus x and minus x in terms of plus z and minus z. So the way I remember this is that when you're writing matrices, these have to match these. These have to match that. So in other words, the v dagger would be more like plus z minus z in terms of plus x and minus x. That's how you have to fill it out. So what is this matrix? Well, that's kind of what I say here. That in general, if it is pointing in some direction, it would look like C and S. And if it's X, it would be 1, 1, basically. So you would write, so this matrix would be something like, I think, 1, 1. And this one actually would be more like 1 minus 1. Now what about this one? Well, here this column is like, what does a spinor along Z look like in terms of x and minus x? Now that would take time to figure out, except that whatever I'm writing here is the conjugate transpose of this. So I really don't need to spend the time figuring it out. I could just transpose it and I'll be done. So I could do something. Now if you did all that, again, the answers would be consistent with this. So those are shown in the lectures, you can look at it, see how it. So this would be one way to think about it. If you accept this, then the rest will kind of follow. Okay? And I think that there is one lecture there which tries to connect the 2 points of view, which tries to justify this. And maybe we can watch it also. But since we have limited time, I'm thinking there is another thing I want to get across quickly, so that we can then after that discuss many other different things depending on your interest. And that has to do with, usually so far, all the developments in spintronics, where you learn how to control spins, came from magnetic contacts. Because magnetic contacts give you these 2 different resistances when it comes to upspins and downspins. Allows you to preferentially inject detect. But these days a lot of interest in a totally different effect, which is related to the spin orbit coupling. And that is what's connected with the spin Hall effect and all that. And that is a totally different way of controlling spins, which is again finding a lot of interest. And that has to do with, you see here, what you have is a magnetic material, a non-magnetic channel, and a magnetic material again. And what we are talking about with spin Hall effect is yet a third type of material, materials with high spin orbit coupling, which would be called non-magnetic materials. but high spin orbit coupling, and that has the effect that so what are these materials? Well, the most common one where there's a lot of interest nowadays is what's called heavy metals like tantalum and platinum, and they have this property that if you run a current this way, electrons, then the up spins will bend upwards, down spins will bend downwards. If you run it the other way, then it will be reversed. Up spins will go down, down. So what you can do is turn a charge current into a spin current, because if I stand here, I see up spins coming up continuously, not down. And of course, what got everyone's attention was these experiments in 2012, like 5 years ago, which showed that on tantalum and platinum, if you put a magnet here and you run enough current, this spin current is enough to actually turn the magnet. And at room temperature. So that's based on the spin orbit coupling. So maybe what I'll do next is we'll just go through a lecture briefly introducing this spin orbit coupling, because then I think we have all the basic things. One is magnets, because magnets essentially let you control spins through the interface resistance. That's it. That magnets means you have a high resistance contact to one spin and low resistance to the other. Whereas spin orbit coupling allows you to do this through this spin charge converter, which we will talk more about. But I want to say a little bit about the spin orbit coupling. Right? So maybe. Welcome back to Unit 4 of our course on quantum transport, and this is the 5th lecture. Now, in this lecture, we want to talk about some of the spin-dependent properties of the channel that come in through this H. Like in the previous lectures, in like 2 and 3, we talked about magnetic contacts and how the spin-dependent properties enter through the self-energy. Now we are talking about the channel. Now, in this context, first want to remind you, like this is something we talked about in part A and also in part B, that usually when you're talking of electrons in vacuum or in atoms, you have a Hamiltonian where this mass is the free electron mass. Now, electrons in solids, of course, in general, its description is much more complicated, but the simple description that we have largely been using for our examples involve this effective mass model, where they are described by a band whose band edge is at EC and whose mass is not the free electron mass M0, but rather the effective mass M. And of course, there is no simple way to derive this from this. And this is not general either. You may have many bands, you might need a more complicated description. But what we have been using for our examples is the effective mass model. Now, in this lecture, what I'll try to show is that when you consider electrons in vacuum, I'll try to explain how the spin orbit correction comes about. And this requires you to take the original Hamiltonian multiplied by I being this identity matrix, 2 by 2 identity matrix. Just as earlier, I took a simple one-level model saying if the level is epsilon, then when you include spin, it becomes epsilon I. Similarly, this part kind of becomes what we had before times I. And then there is this additional relativistic correction, which is what I'll try to explain. That's called the spin-orbit coupling. And this involves these Pauli spin matrices that we have introduced. The sigma, and this F is the electric field. So what I'll try to explain is this relativistic correction and where it comes from. Now in solids, this though is in vacuum or in atoms. Now in solids, there's a similar term, but of course again in solids, the general description could be much more complicated. But within this one-band model, if you consider a conductor in the xy plane so that this z direction is normal to it, then you would have a term looking like this, which is often called this Rashba spin orbit term. And that's what we'll consider. Remembering again that in general electrons in solids may require or you may want to use more sophisticated models. So what we'll be talking about then is largely about this term and electrons in vacuum and what this correction is about. So as I mentioned, this is what you call a relativistic correction, which means originates from this relativistic effect. Now, the non-relativistic energy momentum relation is E equals P squared over 2m. That's the semi-classical equation, and the Hamiltonian you use in a quantum description is obtained from this by replacing the P with the E operator or the momentum operator. And as you know, this leads to this dispersion relation, the EK relation, where instead of P, if you put H bar K, you'll get the EK relations. So this is what you have generally been doing. Now, the relativistic energy momentum relation looks like this. So if you put momentum equals 0, you get E equals mc squared. This is the most famous equation in the world, I guess. And then when the momentum is non-zero, that's when there's this additional term. Now the question is, how do we write down the corresponding Hamiltonian, the H matrix? Because if I turn the P into an operator, I have a problem because you see, I need the operator corresponding to the square root of this. And having an operator under a square root is not very convenient. Right? Now this is where what Dirac showed was that you could write a matrix like this, which this is actually a 4 by 4 matrix in the sense, although it looks 2 by 2, but if you look up here, it's mc squared times I, and I is the 2 by 2 identity matrix. Minus mc squared I, that's again a 2 by 2 matrix. And this is the sigma dot P, sigmas being the Pauli spin matrices, and those are again 2 by 2 matrices. So each one of these is a 2 by 2 matrix, so overall it's a 4 by 4 matrix. And what Dirac showed was that this matrix, if you multiply it by itself, you will indeed get that number times a 4 by 4 identity matrix. So in some sense, it's like the matrix square root of that. So just to see that, what you have to do is multiply it out. So multiply this with this. So then what you get is, if you look at say the 1 term, m0 c square I, m0 c square I. That's like m0 square c to the power 4 I. Then you have c sigma dot p and again c sigma dot p. And that's where you have to make use of this identity that I believe I've stated earlier, that for any vector v like this, sigma dot v1 times sigma dot v2 can be written as the sum of these two terms. And in this case, if v1 and v2 are both this operator p, then you see sigma dot p times sigma dot p becomes this p dot p, which is p square I, and p cross p, which is 0. So this times this becomes like c square p square times I, and so it adds up and gives you that quantity times I. Same with the 2 element, whereas if you look at the off diagonal, this one, you get something like this times this plus this times this, which is exactly the negative, and so it cancels out. So here you get this, what I've written as Z, which is like a 2 by 2 zero matrix. So this, of course, is identity zeros here. That's basically the 4 by 4 identity matrix. So bottom line is, this H is kind of like the square root of that in a matrix sense. Okay? Now, so this is the Dirac Hamiltonian, this that we just wrote down, and it corresponds to an energy dispersion relation that corresponds to this relativistic one. And if you plotted it, it would look something like, when k is 0, the energy would be mc squared, and then as k increases, the energy would increase, like so. Now, if you want to use this, the Dirac equation, if you want to use this to describe systems, then you see you have a 4 by 4 matrix, and you need a wave function with 4 components, which I've written as psi and phi. The psi itself is a 2 component quantity, phi itself is another 2 component quantity. Now, what we commonly use though is not a 4 component wave function, but a 2 component wave function. And that is this non-relativistic approximation that one makes. Let me explain the idea a little bit. So actually, if you look at the energy here, you'll notice there's a plus minus, because when you take the square root, it's a 4 by 4 matrix. So when you look at the eigenvalues, you'll find 2 of them are up here and another 2 down here. And initially, of course, this caused a lot of debate because, how do you interpret all these negative energy levels? And the accepted picture that people have these days is that in vacuum, where there is nothing, that corresponds to all these energy levels being completely filled up. So even when there is nothing, these are all filled up. And then if you have a few extra electrons, those are the ones that we normally see out here. And an important experimental consequence of this picture is that if you hit this with light whose energy corresponds to bigger than 2mc squared, then it can knock these electrons out from here up over here, leaving a hole behind. And that's what's called a positron. That's this anti-electron. And these have been experimentally observed, very real things. But usually, of course, you're not hitting it with light with such huge energies, because mc squared, if you put in the numbers, the free electron mass, the velocity of light, then in units of electron volts, it would come out to be about a million electron volts, or 500,000 electron volts. So this is a very huge energy. And so normally you're not hitting it with light with that kind of energy. And so most of the time, all the physics we see is electrons out here. And this is largely sort of filled up. Now, if you look at the wave functions of electrons out here, the thing is, it is largely psi with a little bit of phi in it. Whereas the wave functions here is largely phi with a little bit of psi. And the reason you can see, if you put p equals 0, then you see the mc squared, that's the top band. That corresponds to the first 2 components. So E psi equals mc squared times psi if the momentum is 0. And E phi is minus mc squared times phi. So this is largely phi. So as long as we are talking of relatively low energy electrons out here, you can use this simplified description where you keep only the one component. Of course, you cannot just drop it because that wouldn't be right. What you could do is this idea that we had used in unit 3 for calculating self energies. You see, there the argument we had is, supposing we had a device described by H and a contact described by HR, and they are connected by this matrix element tau, then you could replace this, you could get rid of the contact and write E psi equals H plus sigma psi, where the sigma is given by this tau G tau dagger. And this is the general method for calculating sigmas. Here, of course, we are not talking of contacts or anything, but you could use the same idea. You could evaluate a sigma. You see, what you want to do is keep this and get rid of this part. So what you could do is calculate a sigma, which is tau, that's sigma dot p, G, which is this E minus mc square plus u, so that's E plus mc square minus u, inverse, and then tau dagger, which again is sigma dot p. So that would be the sigma, and this we could add to whatever we had here, and that would be our effective Hamiltonian. But now it would be 2 by 2 instead of 4 by 4. So instead of the actual direct Hamiltonian, which is 4 by 4, you could use something like this. This is the reduced Hamiltonian, which is 2 by 2. And there we have added in this tau G tau dagger type of term. Now, this requires some discussion then in terms of how to handle it when you have a potential that is varying with energy, varying with spatially and so on, because you see, this itself is a matrix. But what you could do is, one approximation we could make is, we could say that, well, in this quantity here, we'll replace E equal with just mc squared, with the idea that, you see, we are interested in energy levels up here, energies up here, and that's almost mc squared, and a little bit, but near the mc squared. So if you do that, this becomes 2mc squared. And so it goes to this inverse, so that's 2mc squared, and the c square cancels out the one we had before, and so you get this. See? And this, using the, say, this identity I had mentioned before, sigma dot v1 times sigma dot v2. In this case, the v1 and v2 are the same vector. That just gives you p squared over 2m times I. And that's our usual non-relativistic answer. So this is what you get if you do the crude approximation of putting E equals mc squared. But if you try to evaluate this a little more carefully, I mean still approximately, but a little better approximation, then you get this spin orbit term. This is this relativistic correction, that the first order correction to this non-relativistic result. And I'm not going into the details of how you get from here to here, but the point to note is this involves the electric field F. And the electric field is related to the gradient of U, because U is the potential, field is the gradient of that. Now, one way to, I guess, understand this, or I guess one related result that might give you a little more insight into this term, is something like this, that if you wanted to include magnetic fields, then as we discussed in Unit 3, magnetic fields require a vector potential A. The B is this curl of A. And in the Schrodinger equation, P gets replaced by P plus QA. And so, if you include magnetic fields, then in the Dirac equation, P would get replaced by P plus QA. And so when you calculate the reduced stage, you'll get something like this. And this, with a little algebra, I mean, it's not obvious, takes a little algebra to get there, you can show is actually P plus QA dot P plus QA over 2m0I. But there is another term there, mu B sigma dot B, where B is the curl of A. As I say, this isn't complete, this isn't straightforward, it takes a little algebra to get there. But this then becomes this result, and what we had done in B 3.6, of course, we didn't have the spin part of the story at all. What we had was just this. But that would come out of here, of this Dirac equation. If you put P, instead of P, you put P plus QA, and then do the reduction. Then you get this additional term. Now, if you compare this with this, it gives you a little bit of insight in the sense that you could say, well,
this F cross P is almost like an effective B field. So often people say that, oh, the spin orbit term arises because an electron moving very fast in an electric field kind of sees an effective B field, which is F cross P, F is electric field, divided by 2mc squared. And so in a large electric field, you can have a large effective magnetic field, which then gives you something like this. So that is, if you compare this and rationalize it in terms of something like this. But of course, that's not the derivation of this at all. The derivation is what we did in the last slide. That would be the method of how you get there. Now, so to summarize here then, it's like in the Dirac equation, you have a 4x4 matrix H, and if you include potentials, U goes on this diagonal here, and vector potential goes in P plus QA. And if you reduce it using the ideas we talked about, then you get a 2x2 Hamiltonian, which looks something like this. This is what we had before. Now, when you include spin, you get an I in front of it. There's a 2x2 matrix. And then there is this additional part that involves the spin matrices. This is called the Zeeman term, and this is the spin orbit term. So this is for electrons in vacuum. Now, if you want electrons in solids, then this part, I guess you have the EC conduction band edge, and again, we are using the simplified one-band description here. You have an EC, and then instead of the free electron mass, you have the effective mass. And then you have this G factor of the solid that comes in to the Zeeman term. And this could replace, instead of this, you would have a term looking like this, which you could rationalize by saying that, well, if I have an electron confined in this XY plane, there must be an electric field in the Z direction that's keeping it there. If you thought of it that way, you can see why instead of F, you have a Z. And it looks similar. And this eta itself then is the Rashba coefficient, or the spin orbit coefficient. Okay? And as I say, in general, depending on what model you are using for solids, there could be more complicated description. What we'll talk about in this course is just based on this picture. Now, if you do not have any external magnetic fields, then there's no B or A, and so then you get something like this. This is our usual, without any electric fields, that our usual Hamiltonian. That's the I, and then there is this Rashba term for at the surface of a two-dimensional conductor, sigma dot Z cross P. So with that description then, we have the spin orbit Hamiltonian that we want to talk about. So what we'll do in the next lecture is see how you can translate it into the tight binding parameters. That is, what we have done earlier is, we are saying, if you had this simple Hamiltonian, this EC plus P square over 2m, how you can choose your tight binding parameters, the on-site ones, the epsilon, and the nearest neighbor ones, this T, how you can choose it to match the dispersion relation to what you want. And we talked in 3.6 about how you could extend that to include vector potentials. What we'll do in the next lecture is talk about how you can choose these parameters so as to correspond to this spin Hamiltonian that we just talked about. Okay, so that was I guess a very quick introduction to this spin orbit coupling. And this is one of those things that been, I guess in the case of atoms, were identified and understood like back in the 1930s and 40s, that when people try to understand the atomic spectrum, they would see effects that required this spin orbit term that I mentioned, that required this relativistic correction. And it's a real relativistic correction. And the reason it's important in heavy metals, and I mentioned this spin Hall effect that comes
that's in heavy metals like tantalum and platinum and so on, which have this high spin orbit coupling, is that when you go up in the periodic table, in general the spin orbit coupling goes up. Why? Because the understanding is it depends on this electric field that the electrons see. And right around the nucleus, these electric fields are extremely large. And they are particularly large the bigger the nucleus, more positive charge. So when you are like a carbon has very little spin orbit coupling, graphene by itself. On the other hand, as you go up the periodic table, silicon it's a little more, gallium arsenide more, and so on. In general, as you go up the periodic table, the strength of the spin orbit coupling goes up. And this, as I said, in atomic spectra have been noticed. In the case of solids, it has been noticed very well in the case of optical properties, in the sense that, I guess, as you know, usually people draw these EK diagrams. Valence band and conduction band. And if you inject excess spins here into the conduction band, when they jump down to the valence band, they will emit light. That's well known. But because of spin orbit coupling, and the reason, the discussion not obvious, the light that comes out is actually circularly polarized. So, and that is something that was used a lot in the early days in gallium, in doing spintronics on gallium arsenide and all these materials. Like you're trying to inject spin polarized carriers, but how do you know you have spin polarized carriers in there? Well, you look at the light that comes out. Is it circularly polarized or not? Does it have a circular polarization component or not? These days, of course, you can electrically inject, detect, you can measure the voltages with magnets and all that. So it is not as important anymore. But in the beginning, it was like a lot of spintronics used to be on gallium arsenide rather than on silicon. Because on silicon, it's like, well, we don't know how to detect it, because in silicon, it doesn't emit light very efficiently at all. But I've always been amazed by the fact that, here is a common experiment done in laboratories where there's a very clear indication of something that's a relativistic effect. Because normally you don't expect relativistic effects you associate with extremely large velocities, close to speed of light. In a solid, nothing's really moving at that speed at all. Okay? And yet there's a very definite result here. And it comes from the fact that I guess right around the nucleus the fields are extremely high. And because the term that you see is sigma dot E cross P, I guess the general thing is sigma dot electric field cross P. And the one line explanation usually is that because of relativistic effect, this electric field looks like an effective magnetic field. So every electron sees an effective magnetic field. That's the usual thinking. That's the one line description. Now, so this is something that I guess has been known in solids for some time. And some of the effects of this in the context of two-dimensional conductors, one of the effects of this that's established is this coherent, this precession of, that is, if, for example, you inject up spins in this direction from a magnet, then depending on, so let's say you are near a surface, so this is a surface, and the effective magnetic field is the electric field cross P. So if the momentum is in this direction and the electric field is in this direction, then it feels a magnetic field that is in this direction. And so you have a spin and the magnetic field is like this, and the spin wants to turn around it, around that field. So as it goes along, the spin is rotating. And then depending on the direction of this magnet, it may be in just the right direction to get out, or it may not be. And so you could control how much actually gets through. So these are experiments that have been done in the last 5 or 10 years, which show all those things. But these are all relatively delicate experiments that have to be done at low temperatures. But what now seems fairly well established is the spin Hall effect, which is a strong room temperature effect. And this we can discuss more in the discussion session. But the basic fact is something like this. See, we talked about this concept of modes or channels. We mentioned that this is one thing that was not part of general solid state physics. In solid state physics, usually you talk of density of states. But this concept of density of modes or channels has been very useful and is used a lot in mesoscopic physics and nanoelectronics. And this comes from this idea that G equals Q squared over H times M. Now, usually what would happen is that you have, say, certain number of modes going in one direction. You'd have the same number of modes going in the opposite direction. And if this is upspin, then if this is downspin, you'll have the same effects. So this would be what you might call a normal material. Now, what happens in a magnetic material? Well, in a magnetic material, in fact, instead of M, let me actually just put some number. Say 100. Say 100 here, 100 here, 100 here, 100. Now, if you had a magnetic material, then what you might have is say 100 upspins, but only say 10 downspins. Right? Because, and then if you reverse the magnet, this would become 100 and that would become 10. So everything we're talking about in that context could be understood in terms like this. But basically, a magnetic material has a lot more modes or channels belonging to one spin than the other. And that allows you to distinguish between them, have a different interface resistance for each one and so on. Now the spin orbit materials with high spin orbit coupling, and we're talking about generally these two-dimensional conductors with high spin orbit coupling. What you could show, starting from a Hamiltonian like this, if you actually calculated the modes, the picture you would get would be something like this. See, 100 going this way, but relatively few going the other way. So this is an unusual situation. 100. Usually, always in a material, if there are lanes that are going north-south, there's also lanes going south-north. But if you just looked at the upspins, you'll find a lot more of one type than the other. But then it is compensated by the down. So downspins, if you look, this would be 10, and that would be more like 100. And this would be part of, I guess people say, time reversal symmetry. So time reversal symmetry requires that if you have a material, if the Hamiltonian has time reversal symmetry, then upspin going to the right and downspin going to the left should be equal. Those two things are equal, and those two things have to be equal. So this one can actually argue from the nature of the Hamiltonian that had to be. Okay? So that connection can be made. And magnets, though, don't have time reversal symmetry. So number of ups going to the right is different from number of downs going to the left. So magnets don't have time reversal symmetry. But this one does. And there's interest in materials which are actually magnetic as well as high spin orbit coupling. Then I guess then there is no reason why this and this have to be equal. This could be 90, for example. But in general, I believe the total number going backwards should be the same as the total number going forwards. That I think is generally true. But these are all things where people's understanding is still evolving, right? We're still looking at experiments, lots of arguments about various things. But this leads to very robust room temperature effects, just this basic fact. Because from my point of view, it's like if you have one thing we discussed in this course earlier is that when you have a current flow through a material and you looked at the electrochemical potentials, I mentioned that mu plus, that's the occupation of the right-going states, is different from mu minus, the occupation of the left-going states. This is mu1, this is mu2. And I argued that, this is electrons coming from here and all the right-moving states are occupied according to this, left-moving states occupied according to this. You look anywhere, there is more right-going states than left-going. Otherwise, there wouldn't be a current. That's generally true in any material. So anytime there's current flow, the electrochemical potential for right-moving states is higher than the electrochemical potential for left-moving states. But in these materials, okay, for the moment, let's idealize and make the 10s 0. Let's say. Not 10, let's say it's 100 this way, 100 this way, but these are 0. Then you see, anybody going to the right is an upspin. Anybody going to the left is a downspin. So what that means is, mu plus is also mu up. And mu minus is also mu down. So you have kind of created a difference in spin potentials. Upspin potential is different from downspin potential. You have created a spin voltage just by running a charge current because of this difference. Now, of course, if this is not 0, then this isn't exactly this. It's like 90%, mu up is like 90% of this and 10% of that. Mu down is like 90% of this and 10% of that. That's fine. But basically the point is, anytime you run a current, you pick up a spin voltage. And that to me is kind of generally what the spin Hall effect, at least the phenomena itself you can understand in these terms. Now whether there is additional issues and additional phenomena, that again is still debated because there's a lot of argument. The basic fact with spin Hall effect is that there's a whole class of materials, different materials. You run a current this way and you get a spin voltage on the surface. And if you happen to put a magnet on top, that spin voltage will drive a spin current into the magnet. That's the basic fact. And that occurs in a whole variety of materials, not just tantalum and platinum, also in indium arsenide, in the topological insulators, bismuth selenide, bismuth telluride. That's the basic fact. So looking from outside, you would say, okay, all these materials show this basic thing. Now the question is about the mechanism, and what I just described to you, that is a kind of surface mechanism that would explain a lot of this. What isn't clear is, in addition to the surface mechanism, whether there could be other bulk mechanisms. That part is debatable. Right? But just in terms of the surface, you could understand it by this difference. The idea that this 100 is not equal to 10. Whereas in other materials that we know, this is a normal metal, that's magnetic. But these high spin orbit materials are kind of very different in that sense. Okay. So let me stop it now. And I guess in the next session we can have general discussion and questions. And I had a few questions I could already, which I haven't answered yet. To start with those and go on.
So all of you paid registration fee. Is there anyone facing problem paying the registration?